All right, welcome back. Hope you're staying safe and uh, staying far from everyone. So, so this video is going to be a lecture on locating arrays, which is the first topic that we're going to look at after the after spring break. So what we have done so far is we have talked about covering arrays, which for the entire class, and so locating arrays are basically they're based on covering arrays, but add additional constraints that are useful in real world contexts, which we'll see in a second. So what we've been talking about so far are greedy methods, exhaustive methods. We have done heuristic methods. We have done other computational methods. We did randomized methods, and of course the list goes on after that. But the thing that you should note here is that every single one of these methods can be used in the context of locating arrays. So I'm not going to explicitly talk about each one of these, but they can be used here also and have been. But the thing is, locating arrays are considerably harder to analyze compared to covering arrays. And more of the techniques that have been used for locating arrays are computational. So, one thing that you may want to investigate for your project is, can we use locating arrays for whatever project that you're doing? Or maybe say, well, my project idea was for covering arrays and it gets this result, and if I apply it to locating arrays, it gets this kind of result. So I hope that this actually inspires you to not just focus on covering arrays, but also do locating arrays. So the here's the central problem. So if we have a test suite, and let's just say the tests are right here, T1 is here. So these are the rows in the covering array. So the rows in the covering array, and we have a bunch of rows. Let's say we have n of them. And maybe let's say that test one, let's do green for this. So test one passes, test two passes, but test three fails for whatever reason. And then we just say whether it passes or fails for all of them. Maybe say the last one fails. Then clearly, by the fact that test three failed, there is some fault in the system of some kind, purely based on the fact that test 3 failed. If none of the tests failed, then with some degree of certainty based on the strength that we have picked, then we can say that there is no fault. But the fact that a test explicitly failed, there definitely is a fault. Here's the problem though. So the covering array says, well, okay, this test 3 failed, but when we go back to our code or whatever system that we're looking at, how do we actually figure out what the fault actually is? So how can the covering array tell us what, so in quotes, what the fault is? And if we just use a covering array by itself, well, that might not be possible. It is possible in the case where there are very few faults. So let's just say that we have 5 tests here, and let's say that this is the one that fails. Well, what we can do is we can say, let's look into this row and look at the interactions that uniquely happen at that location. And if we know that there's exactly one fault in the system, then we can look at interactions in that row and just test those particular interactions by themselves and not have to test the entire row. So you could do that, but this is quite computationally intensive because remember, for each row, there are k choose t possible interactions. Yeah, interactions that could appear in this row. So then we would have to perform k choose t tests to actually determine what the row, what interaction was causing it. And that's on the assumption that we know how many faulty interactions there are, but there could be many more potentially. So the entire purpose of a covering array is to certify the absence of the fault. So when there is a fault, well, the covering array just says there is one, but it doesn't tell us what the faults actually are. So is a covering array the right thing to do? Well, in some context, yeah, it might be the right thing to do, but maybe we want to actually find what the faults actually are. So the question we want to answer is there a systematic way to recover, whatever it means to recover, the faults, if there are any? So if there are faults in the system, and the covering array says there are some, how do we actually figure out what the faults actually are? So that is something that is called a locating array. So a locating array, in a nutshell, is an array that is a covering array, so it is a covering array, but it has the additional property that we can locate what the faults actually are. Or at least in principle we could. So to do that, well, let's look at a potential problem with this, or at least the motivation of the definition of a locating array. So let's just say we have 5 tests again, and let's say that we have an interaction with these 3 columns and an interaction with, let's say, this column, this one, and this one. And what I'm going to do in blue right here is I'm going to highlight which rows these 3 interactions appear. So let's say that they appear in this row, and then they appear in this row. Well, let's run our test to see and look at what tests pass and which tests failed. So let's say maybe this test passes, this one passes. And then the other 2, the ones that we have circled or boxed, did not pass. Okay? Well, it could be the interaction in red that caused these 2 faults, or it could have been the interaction in purple that caused the faults, or maybe both of them, potentially, or maybe neither of them. But the thing is, well, these 2 interactions appear in the exact same set of rows, so there's no way we could actually distinguish which interaction it could possibly be. If the purple interaction appeared only in the 4th row, then so let's just say that the purple interaction did occur only in the 4th row. And blue means that both of them occurred in the... Actually, no, my mistake. Let's just revert it to what I meant to say. The purple one only occurs in row 4, and the red one occurs in row 2. And in row 4. So this is what I meant to do. So the purple interaction appears in row 4. The red one appears in rows 2 and 4. Well, because these 2 interactions right here, maybe I'll do this in black so it's easier to see. So because rows 2 and 4 failed, it can't possibly be the fault of the purple interaction because it only occurs in row 4. Whereas the red one, if it's the only one to appear in rows 2 and 4, that will be the interaction that causes the fault, or or at least has high confidence that we can assume that it causes the fault because it appears only in the rows that the test actually failed. So so that's the motivation here. If we can guarantee that different sets of interactions appear in different sets of rows, then we could, in principle, determine which interactions cause the fault. So here's the definition. So we're going to let row of T be the set of all rows where T appears. So for the example that we have here, so the red one here is going to be rows 2 and 4, and the row for what color is it? Purple. So the row set for the purple interaction is just 4 in this case. And so because notice that these two sets are different, that allows us to distinguish one interaction from the other. So if we have the property that the two sets are different for every pair of interactions, then, and if there's only one fault in the system that we can at least say a priori, if there's one interaction in the system, then we can recover which fault causes the interaction, because if there's only one faulty interaction, well, it must appear in the rows of some interaction, but the fact that the sets of rows are always different for every pair, we can actually say there must be some interaction, exactly one, that appears exactly in the rows where the tests failed. So in principle, we can determine which interaction causes the fault. Well, we would have to go through the interactions and actually determine that for ourselves, but we don't actually have to run the tests again, which is a good thing. We would just have to go through the interactions and actually just compare the sets of rows where they appear, these row values, against the tests that actually failed. So in the example that we have here, well, rows 2 and 4 failed, and if the thing on the left is a locating array, then we can guarantee that the red interaction is the one that caused the fault, because no other interaction appears in rows 2 and 4 exactly. If we had another interaction that appears, oh, I don't know, so let's just say in a pink interaction that occurs in rows 2, 3, and 4, then we'll test 3 passes. So if there's only one fault, the pink interaction couldn't have caused it. But of course, in a real system, there may be more than one fault. So we're going to make an additional assumption. If we know some upper bound, let's call it D, on the number of interactions that could, the number of faulty interactions, then, well, it could be any set of D, or at most D interactions. So if we pick 2 different sets of interactions of size at most D, and the union of the rows that they appear in is always different than every other set of at most D interactions, then by the same argument, if we know, let's just say like D is equal to 3, then if I pick any set of 3 interactions, the rows that any one of them appears in is unique compared to any other set of 3 at most 3 interactions. And so then when we make our determination, oh, well, this test passed, this one fails, etc., we could, in principle, determine which set of interactions caused that fault. Okay, so let's see. So I'm going to make an additional notational thing here. So note before I had row of T here to be the rows where T appears. And here, if I have a set of interactions, so if D here is a set of interactions, so this is just the union of uh, the row values for each interaction in the set that we have. So look at every interaction in the set of interactions and then just put all of the rows together. So in English, this means all rows where some interaction T in D appears. Okay, because if any one of them appears in a certain row and that row fails, well, that one might be the cause of the fault. Because we may not be able to determine, well, this particular one is the fault causer. It may be this set of three or whatever. So, and then finally, a covering array is DT locating. So D and T are the same as before. So D is the size of the interactions, the set of interactions to compare. And it's the same idea, except here we are forcing that the sets that we pick to have size exactly equal to D, because it's often easier to work with whenever you have the set of interactions having exactly the same size. Whereas when we had the less than or equal to D condition, we have to deal with sets of size D minus 1 or less, and it's often harder to work with. So sometimes we want to look at D bar, T bar locating. So notice the bars on the top here. It just means that it's exactly the same thing, except the sizes of the sets of interactions are at most D instead of exactly equal to D. Okay. When D and T are both 1, so in a covering array, when T equals equal to 1, we know the answer, the optimal number of rows answer. And for a locating array, we know the answer when D and T are simultaneously both 1. But in every other case, apart from very small or there isn't an exhaustive set. So if I have like D equal to 2, T equal to 1, we don't know the answer. But there are some constructions of infinitely many optimal locating arrays for other parameters. It's just that we don't have every single choice of a certain number of columns to know the number of rows. So basically the landscape is more bleak than the covering array case because of this additional constraint here. There is a lot of work here, but there is quite a lot still unknown with this. Okay. But you may be thinking, okay, well, and also we're going to be reading about this paper in more detail in a real world context on Wednesday and Friday. But you may be thinking, well, okay, locating arrays, the condition's actually quite complicated to check because, well, you got to make sure that every choice of D interactions is not appearing in the same rows as every other D set of interactions, which is quite computationally intensive. I invite you to actually determine how intensive that is, but suffice it to say, it's really intensive. In fact, there was a paper that was recently published about actually an improvement to the algorithm and actually checking whether something's a locating array. So it's very difficult. So you may be thinking, okay, locating arrays are just something we don't want to do. Maybe we just want to minimize the amount of time it takes to certify a fault exists. Maybe we don't have to find the actual fault. Maybe we just want to determine that the fault is there. So maybe like if we have a set of rows right here and a fault is on that row right there, so the test will say no, we don't pass. We want to minimize the amount of time that we actually do that. So it may be it's a different question, of course, because we're not actually finding what things are causing the fault, but rather we're just trying to determine whether there's a fault quickly instead of having to um, test everything, which may be too cumbersome. So, uh, so what we're gonna note here is row of t. So row of t here in this context is going to be the first row that covers t. So it's not the set of rows in which it appears, but rather the first one that it appears. So it's a different. It's unfortunately a difference in research areas. So people picked row of t in this. Locating array people picked row of t to mean something else. It just happened to be exactly the same. But row of t here is going to be the first row that covers t. So if t is the only thing that is faulty in the entire test suite, well, we gotta execute that many tests. So if we know that there's a fault on this row right here, well, we gotta execute 4 tests to be able to find it. So because in this array it's in the 4th row and it's the only fault. So let's see. So if every interaction is equally likely to be the faulty one, and we can't make a determination on where they are, then the on average, what's the expected time to find it? Well, it's the sum of all the rows. It's just basically the average row where the interaction appears for the first time. So it's just the sum over all the row values, which is the rows in which they appear, divided by how many interactions there are, which is k choose tv to the t. So in English, this is just the average first row in which interactions appear. Because the row values in this case are just the first time that the interaction appears. Okay. And there hasn't been a lot of work on this. There has been some, though, about trying to minimize this average. Because if we can't make a determination on where the faults actually are, well, we just have to assume that every interaction is equally likely to be faulty. So we want to minimize the average in that case. So the thing that we would want in this context is to minimize this value. Okay. So basically we want to minimize the row of t values because the term on the front is never going to change. The number of interactions never ever changes. So we want to minimize the sum of the row of t values. So I'm not going to go through all of this, but there is something that we can do here, which is if we know that there are a certain number of faulty interactions in the system, then it is possible to calculate what the expected number of tests actually is. So this is actually just a generalization of the case where we had exactly one faulty interaction. So here I should say before s is equal to 1. And if you check, well, it's exactly that. Here, I'm just saying that T of I is the number of actually, I have this wrong. Not the number of faults. If we knew the number of faults covered in a row, then we don't need to do any of this computation. This should be interactions. That was my mistake. And I will correct it when I upload the PDF. So let tau of I be the number of interactions covered in row I for the first time. And U of I is just the number of interactions covered later, from row I down. And if there are S faulty interactions and we don't know anything else about where they are, well, we can calculate what the average number of rows that we actually need to consider before, on average, we can detect a fault being there. If we know that there are S faulty interactions. And you could generalize this to say, well, if there are at most S, if there are at least S, and we could derive a different expression, but we could calculate it if we wanted to. Okay, so the reason why I wanted to talk about this is this. So we have three competitors right here, and for the first one we have an array which is optimal. So in this scenario, this example, we have k equal to 11, so that's what the exponent means. T is equal to 3 because I wrote it there, and the 2 on the bottom means that there are two symbols. And it turns out that the fewest number of tests possible, and this is shown through exhaustive computation, is 12 rows. That's the best you can possibly do. And you can see that right here, because whenever we have 0 faults, on average, we're going to have to execute every test, and there are 12 of them. So that's why there's a 12 there. So there is a, if we apply, say, the density method, we get 18 rows. And through exhaustive computation, what people have found is that the best phi of 1 value, which is when s is equal to 1, so when we determine that there's exactly one fault in the system, then we get 14 rows out of it. And then what we're looking at here is if we assume that there's 1 fault, 2 fault, 3 faults, 4 faults, etc., what is the average number of tests that we need to execute in order to determine the existence of a fault on average? So if there's exactly 1 fault in the system, the fewest test one says, I can do it in 5.42 tests. The greedy one says 5.74, and that one says 5.39. And we have other values if we assume that there are 2 faults, 3 faults, 4 faults, etc. Okay, so the thing that you should note here is that apart from, let's see, so from this point on, so from 4 faults on, it looks like the most greedy one is the winner. So the thing we want here to remember is to minimize the average. Well, we're giving the averages here, so we want the one with the smallest one, which is going to be most greedy. It is not quite as good for a smaller number of faults, but for a bigger number of faults, it's better. And that's because it covers things earlier. And so that's one of the reasons why greedy is good. So you may be thinking, well, okay, well, if I have a test suite right here, and I determine that that there are no faults in the system, so this one says yes, 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 yes. So every test passes. So this tells us that there is no fault in the system. Well, it's just, you may be thinking, well, okay, well, that's just the opposite problem of certifying that there is a fault in the system, because a fault in the system, well, one of the tests passes, or at least one of the tests at least did not pass. So a fault not being there, every test passes, and a fault being there means that some test failed. But it is not true that these are correlated to each other. And in fact, they, in some cases, have completely nothing to do with each other. So the smallest array, the one with 12 rows, so the n equals 12 one, is unique. So that was done through exhaustive computation, not by me, but by other researchers. So it's unique. And the values given are the smallest fault detection rates possible because the array is unique. So for 12 rows, since the array is unique, you're not going to get any different detection rates because it's on average what you're, because it's always an average. And no matter how I order it, it's going to do exactly the same thing. And in fact, they were able to show that through exhaustive computation. Through every reordering of the rows, do we get any different detection rates of faults? And it turns out that the one that they have right here, the the one in the top row, that's the best that they could possibly get out of it. And um, for the greedy array that has more rows, so it has 18 tests instead of 12, but based on this table up here, it has the best detection rate because from 4 faults on, it has the smallest one. Um, but it has been shown that an array could be neither the smallest one nor the most greedy and still have the best fault detection rates. So in this case, greedy happened to win, but it turns out that there are other methods that are not greedy nor have the fewest tests, but still have the best fault detection rates, or at least better fault detection rates than these other two methods. Um, and what has been shown to be better is just use the greedy method, but add heuristic search on top of that. And by heuristics, I mean what we've been talking about. So hill climbing, simulated annealing. A question that I'm not sure has been tried is genetic algorithms. I haven't seen anything on that. It might be worth looking into to improve performance on top of this. Okay, so that's what I wanted to say on locating arrays. So if you have any questions, please post them on Slack. And otherwise, we're going to be reading the paper from Aldaco et al. On locating arrays for Wednesday and Friday. So I'll see you then.